Hello and welcome. We know there are many processes during which, many electrical processes in which, like charging, discharging of a capacitor, heat is released. And so we are moving towards such kind of processes in which heat is released, and we need to find how much amount of heat is released in a particular processes like this. So we have a simple problem at hand, that is an uncharged capacitor with a capacity C equals 4 microfarad was connected to the terminals of a current source, voltage source, with an EMF Xi equals 200 volt. How much heat was released during the charging of the capacitor? This is a simple problem, most simple. And of course we can solve it according to the processes of law of conservation of energy. And we know one such law is the first law of thermodynamics, and that is simply heat given to the system equals increase in internal energy plus work done by the system. But in our cases, we are going to regard capacitor as the system and voltage source as an external agent. So we got in fact heat is being done on the system instead of heat is being done by the system. In this case, our battery does work on the capacitor, so this is basically the heat is basically the work done by the system, work done on the system by the external agent or by the surrounding. So, and heat is revolved, heat is released. So we would like our first law of thermodynamics as heat released equals change in internal energy of the system of the capacitor, that is basically the change in potential energy, electrostatic energy of the capacitor. So this is final potential energy minus initial energy plus work done by the system. But we have the work done on the system, and that should be written with a minus sign. And we can this is basically, I would like to remind you that I'm considering the voltage current source of the battery as external agent, part of surrounding. So I have written here work done by external forces or whatever it is. And if you can rearrange them, we can simply write as work done by external forces plus initial potential energy, and this is work done by external agent plus initial potential energy equal to final potential energy plus heat released. And this is one of the equations we are going to use again and again, or we can write it in one more form, that work done by external agent is equal to change in potential energy of the capacitor plus heat released. We can use this equation as well. And you can see in our case, in this case under consideration, the initial potential energy is being 0, and the final potential energy becomes simply half C Xi square. And work done by external agent, we should be a bit careful writing this expression. This is simply change in charge through the source in positive direction. Positive direction means negative terminal to positive terminal, what amount of charge is flown and in the process. and multiplied by the EMF of the voltage source, and this is the work done by external agent. And so charges flown in our case from negative terminal to positive terminal of the battery is of course CE. So external work done by external agent becomes simply as CE square. And now we can put everything in this equation, and we will get CE square equals final potential energy is half CE square, initial was 0 plus Q, and that gives Q equals simply as half CE square. This is a well-known result, and it can be seen that the efficiency of such charging is 50% only. And thank you very much for watching. The problem is solved, and we are going to solve many more problems like this, and when the problem comes we will find the solution.